So we can start now. So welcome to the session in Materials for Electronics. It's a pleasure to introduce Hagen Klauk from the Max Planck Institute for Solid State Research in Stuttgart, in Germany. So he is a key reference in organic electronics, in particular in organic effect transistors. He has been advancing the performance of these devices for many years, making them smaller, faster, and better, you will see. And also he has been working in the integration of organic effect transistors in flexible semiconductor technologies. So we are very happy to have you here. So I am willing to listen to your talk.
Thank you very much. Good afternoon, everyone. Thank you very much for the introduction and more importantly for the kind invitation. My name is Hagen Klauk, and I've been head of the Organic Electronics Research Group at the Max Planck Institute for Solid State Research in Stuttgart in Germany since 2005. At that time, Esther was still there. So my office is here. Where was your office? Do you remember? Was it somewhere? I think somewhere here, right? Yeah. Good times, Esther. So we had a very productive 2.5 years that we overlapped there before you came here. And so double pleasure for me to be here today and have the opportunity to tell you a little bit what my group and I have been doing since Esther left. So we've been working on organic transistors for the most part. That's interesting. That was working. Let me check. Now, right now. Aha, thank you. I appreciate that. Thank you very much. So organic thin film transistors are field effect transistors in which the semiconductor is a thin, usually polycrystalline layer of conjugated organic molecules, shown here in green. And the operational principle of organic thin film transistors is identical to those of field effect transistors based on any other types of semiconductors, including silicon MOSFETs, by applying an electric potential difference between the gate electrode and the source contact, called the gate source voltage. An electric field is established across the gate dielectric that causes the accumulation of a thin layer of quasi-free charges in the semiconductor layer, shown here in red. And by simultaneously applying a voltage between the drain and the source, called the drain source voltage, we can make these charges flow from the source to the drain and thereby establishing a drain current. And the magnitude of that drain current depends over many orders of magnitude on the density of charge carriers accumulated here and thereby on the gate source voltage. So field effect transistors are essentially voltage-controlled current sources, and they form the basis for every electronic circuit and system that we have come to use over the past, 60, 70, 80 years, I guess. And the reason we're interested in organic thin film transistors is that unlike transistors based on inorganic semiconductors, organic transistors can be fabricated at much lower temperatures. So all the transistors that I'm going to talk about today have been fabricated at temperatures no higher than approximately 120 degrees Celsius. And the ability to fabricate field effect transistors at sufficiently low temperatures makes it possible to fabricate these transistors and integrated circuits and electronic systems based on them on practically any type of substrate, including substrates that would not withstand the higher temperatures required for inorganic transistors, including plastics and even paper. And the ability to fabricate electronic functionality on flexible substrates, of course, immediately leads to the possibility of implementing flexible, rollable, foldable, active matrix displays based on organic transistors and organic light-emitting diodes, as shown in these two examples here. This is a schematic circuit diagram of an active matrix organic LED display. You see the red, green, and blue organic LEDs arranged in a very dense matrix. So regular for mobile phone displays, for example, contain approximately 10 million of these organic LEDs. And from an electrical point of view, electrical engineering point of view, the important aspect here is that every single one of these organic LEDs is controlled by a circuit consisting of one or several thin film transistors. And if you ever thinking about getting rid of your old phone, before you throw it away, take it apart, and you'll actually be able to see the transistor circuit underneath each and every one of these approximately 10 million organic LEDs. So you'll see the individual transistors forming the circuit, the task of which is to control the emission from each and every one of these 10 million LEDs independently of each other. So the controlling the state of emission of every individual one of these organic LEDs is by means of this so-called select transistor. So by applying a row voltage, the transistor switches from the non-conducting to the conducting state, and that causes a drain current to flow through the transistor, which in turn charges this internal pixel capacitor, okay? And this charging, of course, the charge on that pixel capacitor then controls the emission from that organic LED. Now that charging, of course, doesn't happen instantaneously. It takes some time to develop that charge. And the charging dynamics then is controlled by this exponential equation. And then once the pixel has been charged, the transistor is turned off. So the transistor is now in a non-conducting state. And so this causes the charge to be trapped on this pixel capacitor. And this is important because now the organic LED will continue to emit brightness even though we are no longer controlling the transistor. And that buys us the time that we need to address all the other approximately 1,000 or 2,000 rows of the displays to build up an entire image. So the important thing here is that the transistor has a relatively high drain current. And here, the key is that the transistor has ideally a drain current of 0, so that as little as possible of that charge is able to leak away, okay? And from these two exponential equations controlling the dynamics of the charging and discharging of the pixel capacitor, we can derive an equation for the minimum ratio between the resistance of the field effect transistor in the on state and in the off state. Except we're not calling this the ratio of the two resistances, we're calling this the ratio of the two drain currents, which is equivalent. And so we can easily see that this ratio depends on these two quantities, the number of rows of the display, so that's essentially the display resolution, and the maximum pixel charge error that we are willing to accept. So that error is never going to be 0, or else it would take infinite amount of time to charge and discharge the pixel. But as long as we are willing to accept a sufficiently small error, we can solve for this equation. And when we do that, I can plot the results of that equation in this plot, where the x-axis is the display resolution, given here by the number of rows. So most mobile phone displays have a resolution of 2,000 to 5,000 rows, and the pixel charge error that we are willing to accept. And it turns out that the human eye, one of the few things that the human eye is actually really good at, most of the things you have to agree the human eye is really bad at. But one of the things that the human eye is really good at is distinguishing even minute differences in brightness, okay? And so this pixel charge error needs to be really, really small in order for a mobile phone display to have really high quality. And so we can easily see that the minimum on-off current ratio required for active matrix mobile phone displays is on the order of 10 to the 8 to 10 to the 9. Ideally, actually on the order of 10 to the 10, okay? So right there, we have the first item on our shopping list. To minimize the pixel charge error, the TFTs must have a very large on-off current ratio, ideally something like 10 to the 9 or 10 to the 10. Okay, so how do we get there? Well, the on-off current ratio is, as the name suggests, the ratio between the on-state drain current and the off-state drain current. So for the on-state drain current, we can write down an analytical equation from the textbook, and we can solve it by, or we can solve an equation by substituting for the effective charge carrying mobility with this equation that contains the contact resistance, and then we get this equation for the drain current that depends only on physical parameters. And so, let me just point out here. So the L is the channel length, so there's a distance between the source contact and the drain contact. That's the distance that the carriers have to flow through the semiconductor in order to get from the source contact to the drain contact. And this is the gate dielectric capacitance here. And then the contact resistance is a parasitic resistance associated with the junction between the metal source contact and the organic semiconductor layer here, and the metal drain contact and the organic semiconductor here. So heterojunctions are always associated with a parasitic resistance, and we lump these resistances into these values, source and drain resistance, and we find them here as the contact resistance in this equation. So in order to be able to do anything useful with this equation, I have to make a few assumptions for some of these parameters. So I'll set the capacitance of the unit area capacitance of the gate dielectric to a value of 0.7 microfarads per square centimeter. And I'll set the gate source voltage, the gate source voltage and threshold voltage and the drain source voltages to these values. And I do that for no other reason that these happen to be the values that we use in the transistors that I'm going to show in just a few minutes. So we'll be able to compare the analytical results to experimental data. And I'll set the channel width for the same reason to a value of 80 microns. This is a photograph of the transistors that we fabricate, and the channel width here just happens to be 80 microns. And I'll set the intrinsic channel mobility to a value of 1 centimeter squared per volt second, again, because that happens to be approximately, order of magnitude, the value for the intrinsic charge carrier mobility that we see in the semiconductors that we utilize for our transistors. More on that later. And so the only two parameters rather, for which I have not yet assumed values are the channel length and the contact resistance. And so I can now find solutions to this equation and plot them in this graph where the x-axis is the channel length. And I'll use the contact resistance here as a parameter for these 6 different. So I'm assuming 6 different values here for the contact resistance. And so from this graph, we can easily see what we need to do in order to maximize the drain current. One is we need to minimize the channel length. Well, that's not very surprising. And the other is we need to minimize the contact resistance. And that's also not all that surprising. What may be surprising is that below a certain value of the channel length, the on-state drain current is actually independent of the channel length. And this is we see that here, if the channel length becomes really small, then this equation can be simplified to this equation. And it turns out that now the drain current is independent of channel length. And this is basically what we see here, right? We see a saturation here, right? So for large contact resistances, there's going to be a saturation in terms of drain current. So minimizing the channel length below a certain value will no longer result in an improvement in on-state drain current, except if we find ways to minimize the contact resistance. In that case, any reduction in channel length will give us an improvement in on-state drain current. So this is important. Okay, so I'll add this to my shopping list here. To maximize the on-state drain current, we need to minimize the channel length and we need to minimize the contact resistance. And I've chosen these two values here as sort of goals to go after. Now, again, the on-off current ratio is the ratio between the on-state drain current and the off-state drain current. So we've just looked at the on-state drain current. Now let's have a brief look at the off-state drain current as well. So that needs to be as large as possible. We want the transistor to be conducting in the on-state, but basically to be a perfect insulator in the off-state. And there are two main contributors to the off-state drain current of any field effect transistor. One is a leakage current through the gate dielectric. So either directly from the gate electrode to the drain current here, or from the source contact through the gate dielectric and then across the gate electrode and then from there to the drain current. So in measurements, these are difficult to distinguish, but it doesn't make a difference because in both cases, the current here leaks through the gate dielectric. Now, I know what you're going to say. You're going to say, well, wait a minute, the gate dielectric, that should be a perfect insulator. So that contribution should be basically zero. Well, pretty close. So we've spent a lot of time over the last, 5-8 years trying to optimize the properties of the gate dielectric. So that sounds boring. How do you optimize an insulator, right? There's not much to do. But it's kind of important for thin film transistors. So the gate current is the product of the gate current density and the overlap area. So in order to minimize the gate current, we need to minimize the gate current density and the overlap area. So this is a plot of the current density, so basically J, as a function of applied bias for gate dielectrics in transistors where we've used different parameters to grow or to establish the aluminum oxide gate dielectric. And you can clearly see that for the optimum conditions here, we are able to achieve gate current densities below 1 microamp per square centimeter at the regular bias voltage of 2 or 3 volts. Okay, so that's pretty good. And the other parameter then here again is the overlap area, and we're minimizing that by minimizing the distance by which the source and the drain contacts, those are the white regions here, overlap with the gate electrode, which is a little bit difficult to see because it's buried underneath the organic semiconductor here, but you can maybe see it here. So the overlap lengths are these LOVGS and LOVGD values here. And so we're making these as small as possible. So in this case, they're about 100 nanometers rather. And so for these particular values, we get, so again, the current density is on the order of 10 to the minus 8 amps per square centimeter, as I had shown. And when we make the overlap area on the order of 100 square microns, that gives us an absolute gate current on the order of about 10 femtoamps. And that happens to be the resolution limit of the measurement setup that we use in our lab. Okay, so it turns out that at the current state of affairs, we're right at the resolution limit of what we can measure. So even if we were able to make further improvements in reducing the offstate drain current, we wouldn't be able to measure it because it would be below the Loy's limit. Okay. So third item on the shopping list here, minimize the offstate drain current, means we have to minimize the gate current density and we have to minimize the gate contact overlaps. Okay. The second contributor to the offstate drain current of a field effect transistor is leakage current through the semiconductor. Okay, so this is current that doesn't flow through the gate dielectric. So even if I have a perfect gate dielectric now, there will still be some leakage current from the source contact to the drain current when the transistor is in the nominal off state. And I hope that's not too difficult to understand, right? We're asking the semiconductor to be really conducting when we turn the transistor on, but now we're asking it to be a perfect insulator when we're turning the transistor off. So that's a difficult thing to do for any semiconductor, right? Imagine you have to be a semiconductor and you have to do those two things simultaneously. It's difficult. And here's the problem. So this is a band diagram of the field effect transistor. This is the source contact here. This is the drain contact. And in between, we have the organic semiconductor layer. So now let's assume I choose the semiconductor so that the highest occupied molecular orbital here lines up nicely with the source contact and with the drain contact. And I apply negative voltages, so the transistor is in the on state. So the transistor is turned on, so I get a whole current flowing here from source to drain. This is my on state drain current. So this is going to be, a microamp, 10 microamps, 100 microamps, whatever. And at the same time, I have an energy barrier here that blocks the flow of electrons. So the on state drain current is made up completely of these holes. So now I'm going to turn the transistor off. So to do that, I choose the gate source voltage to be positive, or at least greater than 0. So now I establish an energy barrier here, and that blocks the flow of holes from the source contact into the highest occupied molecular orbital. So I'm effectively blocking the flow of holes to turn the transistor off. But at the same time, I'm now making the barrier here that is blocking the flow of electrons from the drain into the LUMO narrower. Right? You see this, right? It's a triangle now. Here it was relatively wide. Now it's relatively narrow. And so I'm going to get undesirable injection of electrons from the drain into the LUMO. And that will be a contributor to off-state drain current. This is one of the major enemies of making a good thin film transistor. And the only way to fix that would be to choose a semiconductor with a larger energy barrier here for the undesirable injection of electrons from the drain into the LUMO. In other words, a semiconductor with a larger band gap, with a larger HOMO-LUMO gap, okay? The larger, the better. And I don't know if you heard about zinc oxide transistors. They're amazing transistors in the sense that they have basically 0 off-state drain current. And one of the reasons is that in zinc oxide, electrons can basically not, it's the other way around. The holes can basically not flow. And so this form of undesirable injection is essentially impossible in zinc oxide. And this is one of the reasons why zinc oxide TFTs have amazingly low off-state drain currents. Now in organic semiconductors, that's a little bit more difficult. And so we're all the happier that Professor Takemir has been providing us with this fantastic organic semiconductor, diphenyl dinaphthothiophene, and I'm only going to call it diphenyl DNTT for the past 10 or 15 years or so, which has a band gap of approximately 2 or 3 electron volts. So it's a relatively high band gap that allows us to minimize, as I'm going to show in a minute, the offset drain current of our transistors to almost the noise limit. But if I had one wish left before I die, it would be a semiconductor that has all the properties of diphenyl DNTTs plus a somewhat larger band gap. And we would be able to minimize the off-state drain current even further. Okay, so next item on my shopping list here, to minimize the off-state drain current, we would be asking for a semiconductor with a as large as possible homo-LUMO gap. Okay, so far I've only considered the static properties of the transistor. What is its resistance when it's in the on state, and what is its resistance when it's in the off state? And that will allow us to build up an image on our display and enjoy a nice still frame. But of course, that's only half of what we ask our displays to do. Really, most of the time we want to watch videos, fast videos. So we also need to consider the dynamic properties of the transistors. Okay? So when the transistor turns on to charge the pixel, we want this to happen as quickly as possible. And when we turn the transistor off to keep the pixel from discharging, we want that to happen as quickly as possible as well. And so we'll use the same two equations there that govern the charging and discharging dynamics. But this time, we're going to solve for the minimum frequency at which the transistor needs to switch between the on state and the off state and back from the off state to the on state in order to allow us to be able to see a smooth video on that display. Okay? So Ft is the transit frequency of the transistor. And from the two equations that I've just shown, it follows that this transit frequency need to be at least have this value, where m, again, is the display resolution. So the number of rows of the display, where, again, most displays will have resolution anywhere between 2,000 and 5,000 rows. And f frame is the frame time. So this is the time that we have available to build up one image. Okay? And I already mentioned that the human eye is only really good at one thing. It's really bad at most of the other things. And one of the other things it's really bad at is the fact that the human eye updates our brain only about once every 10 milliseconds about any visual changes. Okay? Which means it's sufficient if we update our display about once every 10 milliseconds or maybe once every 5 or 2 milliseconds. Okay? We don't have to update the image every microsecond, every nanosecond. That's not necessary. And so if I plot solutions to this equation here, again in this graph, where x is the display resolution and y is the frame rate, we can see that for frame rates on the order of 100 hertz or so, the transistors, the TFTs that control the charging and charging and discharging of the pixel capacitors need to have transit frequencies on the order of approximately 10 megahertz here. Okay? Okay, so next item on our shopping list here. To maximize the display resolution and the inverse of the frame time, the transistors need to have a high frequency on the order of approximately 10 megahertz. So solving for the transit frequency is a little bit more tricky. There's a fundamental equation for the transit frequency of a field effect transistor, regardless of any of the physical or materials parameters. And we can solve for that. We can then substitute for the different values here, blah, blah, blah. We have to make a few simplifications, few assumptions here, and then eventually we arrive at this equation here. It looks like a very complex equation, and it actually is. But okay, if we want to get anywhere, we have to use this equation. Okay, so the transit frequency is going to be dependent on these 8 different parameters here. Again, like in the previous case, I have to make a few assumptions in order to be able to do anything useful with this equation. So I'll choose the same values again for the gate capacitance and the gate source and drain source voltages. And again, I'm going to use a value of 1 centimeter squared per volt second for the intrinsic channel mobility. And this time I'm going to use a value of 300 ohm centimeters for the width normalized contact resistance. And the reason I'm using these two values is that these happen to be the values that we extract by performing the transmission line method analysis on the transistors that I'm going to talk about in 1 minute. And now, the only 2 parameters in this equation for which I have not made any assumptions yet are the channel length and the gate overlap. Okay, so purely dimensional parameters, physical parameters of the lithography that we use to fabricate the transistors. And so we see that in order to be able to achieve a transit frequency on the order of 10 megahertz here, it's immediately clear that we will succeed in that only if the transistor has a channel length that is smaller than 1 micron and gate overlaps that are smaller than 1 micron. Okay. If the lateral dimensions of the transistors are greater than 1 micron, will never be able to achieve a transit frequency of 10 megahertz for these parameters. Okay, that's essentially what we get from this plot. Okay, so a final item on our shopping list here: to maximize the transit frequency, we need to have a very small channeling, very small gate overlaps, less than 1 micron. So nanoscale transistors, or else we'll never make it. And it's immediately clear that that inkjet printing, for example, is never going to make it, right? So with inkjet printing, it's possible to make fantastic organic transistors. So this is a photograph of an organic TFT fabricated entirely by inkjet printing, and this is a photograph of a 10 by 10 centimeter square array of integrated circuits based on organic transistors fabricated entirely by inkjet printing. All the layers deposited and patterned by inkjet printing. Beautiful circuits, device, everything functional, except with inkjet printing, the lateral resolution is necessarily on the order of 10 microns, not below 10 microns. And so the transit frequency will never be above about 1 megahertz, much less 10 megahertz. Okay. And another technology is stencil lithography that we have put a lot of effort into last 10 years or so. In stencil lithography, we use these silicon stencil masks. These are 20 micron thick silicon membranes into which we open holes in specific locations by a combination of electron beam lithography and deep reactive ion etching. And then we use these masks to deposit the functional materials, the gate, electrodes, the source and drain contact, organic semiconductor, through the openings in these masks. We build up the transistor layer by layer. And with these masks, we have a resolution on the order of 1 micron. And that can get us into the range of transit frequencies on the order of about 10 to 20 megahertz. But to have any hope of ever getting beyond that, we have to move to electron beam lithography. Now, I realize electron beam lithography is not a high volume mass manufacturing technology yet, although I wouldn't put money down that it may not be in 10 or 20 years, okay? Electron beam lithography sounds like an expensive proposition, but it's only because there's only like 2 or 3 companies that make e-beam lithography systems, right? If more companies get into the game and they develop new approaches, like with multi-beams, for example, massively parallel beams that would speed up the patterning, e-beam lithography might become a mass production tool in just 5 or 10 years, okay? Okay, but for the time being, we use this right machine to fabricate organic transistors on flexible plastic substrates with resolution on the order of 100 nanometers. So gate channel length 100 nanometers and overlap on the order of 100 nanometers. And these are the measured transfer curves of diphenyl DNTT transistors with channel lengths of 150, 200, 300, 700 nanometers here, and overlap of 100 nanometers. And you see the on-off current ratio here is on the order of 8 orders of magnitude or so. And the off-state drain current here for the transistors with channel lengths of 300, 700 nanometers is in fact at the noise limit of 10 femtoamps. So it couldn't be any smaller at this point, right? But we also see that when the channel length drops below 300 nanometers, the off-state drain current increases by an order of magnitude by going from 300 to 200 nanometers, and by another order of magnitude by going from 200 to 150 nanometers. So clearly, when a channel length is below 300 nanometers, something bad happens. And that's not too surprising, because when we make the channel length too small, we induce basically tunneling through this barrier of holes from the source contact into the HOMO gap, okay? Into the highest occupied molecular orbital, okay? So this is very counterproductive, obviously. And in addition, we induce the injection of electrons here into the LUMO, not into the highest part of LUMO, but into this part here. And that will also then lead to this additional off-state drain current. And so even though the equation for the transit frequency predicts that we should make the channel length as small as possible, there's a limit in terms of how small we should be making the channel length if we want to be able to maintain the minimum possible off-state drain current here, and that limit is currently on the order of 300 nanometers. Okay. Now this is not new. This was developed for silicon MOSFETs about 60 years ago, and it was reiterated for organic transistors about 20 years ago. Okay, so this is not news. But it means that for the time being, for our transistor technology, the optimum in terms of channel length is on the order of 300 nanometers. That will give us the best compromise between the highest transit frequency that we can expect while minimizing the off-state drain current at the noise level. So this is how we make the transistors. It's basically a 5-step process. It takes about 1 week. So we deposit the gate electrodes, pattern them by electron beam lithography. We use aluminum because that allows us to grow a very thin layer of aluminum oxide simply by plasma oxidation on the surface of the aluminum gate electrode. That is our gate dielectric. Has a thickness of about 8 nanometers. Then we deposit the source drain contacts, pattern them by electron beam lithography to minimize the channel length and the overlap here. Then we functionalize the surface of the semiconductor and of the metal electrodes with these organic monolayers here. And then the last step, we deposit the organic semiconductor, our beautiful diphenyl DNTT. Yeah, and then those are the measured current voltage characteristics of such a transistor, having a channel length of 300 nanometers, gate to source and gate to drain overlaps of 100 nanometers, and a channel width of 80 microns. So the first thing we see is that the gate current is in fact very small. Okay, so it's about a picoamp here. So that is a manifestation of the high quality of the gate dielectric, despite the fact that it's only 8 nanometers thick. The second thing we see is that the offstate drain current is in fact at the noise limit of 10 femtoamps. So that's good. And that's a testament to the fact that the offstate leakage current, both through the gate dielectric and through the semiconductor, is in fact as small as we can hope for it to be. The on-state drain current here is 100 microamps. And so the on-off current ratio is 10 orders of magnitude. So this is the highest on-off current ratio that's been reported for organic TFTs. And it's actually higher than for many zinc oxide transistors that we're able to find in the literature. It's, so this confirms the equations that I was using just a few minutes ago. Okay, and then those are the output characteristics, where the drain current is plotted as a function of drain source voltage. Okay, so we fabricate transistors with channel lengths ranging from, as you've seen, from about 200 microns to about 700 microns. And we characterize all of them. And then by plotting the parameters that we extract from the transfer characteristics as a function of channel length, we can extract values for the intrinsic charge K mobility and for the contact resistance. So these two parameters are not accessible by measuring just one single transistor. But by measuring transistors of different channel lengths, we can solve for the channel length, and thereby we can then solve for these two parameters. And the values that we get are values of 1 centimeter squared per volt second for the intrinsic channel mobility, and a value of 300 ohm centimeters for the contact resistance. And so this is why I was using these values earlier in the numerical analysis. Okay. But now, most importantly, to the dynamic performance of these transistors. Remember, most of what we've done here was done with the intention of maximize the transit frequency, of being able to operate these transistors with as high a transit frequency as possible, ideally a transit frequency greater than about 10 megahertz. And so here, to measure to measure the transit frequency of a field effect transistor, what we do is we actually make two transistors and we connect them in series so that we can use one of the two transistors as the one that switches, and the other one as basically as a load, as a resistive load, so that we can get the voltage response here at this output node. And then we use a function generator to apply a step function here in blue to the input of the transistor. And then we use a high impedance probe and a fast oscilloscope to measure the response of the transistor and the output. So the output is inversed. So this is actually an inverter, but we don't use it as an inverter. We use it to measure the dynamic response of the inverter. Okay, so the input should be a step function, and the output should ideally also be a step function, but in reality, it's an exponential function, as I've shown earlier in this equation, right? And then by fitting an exponential function to this response here, we can extract the characteristic delay, and that is in this case 12 nanoseconds, and that corresponds to a transit frequency of 40 megahertz. Okay, so these transistors have a transit frequency of 40 megahertz. That's the highest transit frequency that's been achieved for organic transistors fabricated on flexible substrates. And in the final slide, I want to put this into perspective. So on the left, I'm again plotting the on-off current ratio as a function of contact resistance, and on the right, I'm plotting the transit frequency as a function of contact resistance. And to obtain these two plots, to produce these two plots, I'm again using the two equations that I've shown earlier, the one for the drain, for the maximum on-site drain current in the first part of my talk, and then the one for the transit frequency in the second part of the talk. And what we see is that not surprisingly, as we reduce the contact resistance, the on-off current ratio of the transistor improves. So this is where we are now. This is what I've just shown you. So for a contact resistance of 300 ohm centimeter, we obtain an on-off current ratio of 10 orders of magnitude. Now let's assume that by making additional improvements to the materials that we use in the transistors, let's assume that we're able to bring down the contact resistance by 1 order of magnitude, so something like 10 ohm centimeter. Then using this equation, we can expect an improvement by a factor of 5 in on-off current ratio. So this will be a huge further improvement. So there's a lot of incentive to further reduce the contact resistance of the TFTs. But it gets even better in terms of transit frequency. Similar exercise here. So we're currently here at a contact resistance of 300 ohm centimeter and a transit frequency of 40 megahertz. And again, if we were able to bring down the contact resistance by an order of magnitude, something like 10 ohm centimeter, we could expect transit frequencies on the order of 200 megahertz. So there's two reasons, there are two big incentives to continue working on reducing the contact resistance. And in my personal opinion, this parasitic contact resistance at the interface between the metal contacts and the organic semiconductor layer is currently the biggest impediment for making further improvements in both on-off current ratio and transit frequency. Okay, just if I have, do I have 2 more minutes?
Yes.
Okay. Well, you know what, then I'll skip this. Okay, so the idea was I was also going to talk about N-channel TFTs, but then I'll skip that and I'll come straight to the summary. So the idea of this was to convince you that organic thin-film transistors are potentially useful devices for flexible electronics applications. The main reason being that we are able to fabricate them at relatively low temperatures, no higher than about 120, maybe 150 degrees Celsius, and therefore on a variety of flexible substrates, including plastics and paper. And by choosing proper organic semiconductors, it is possible to fabricate both P and N-channel organic transistors. Okay, today I only talked about the P-channel transistors. Maybe if I come back in 40 years, I'll talk about the N-channel transistors as well. And despite the fact that the charge capabilities in organic semiconductors are extremely small, as you know, on the order of 1 centimeter squared per volt second, as you've seen, and despite the fact that the contact resistances are much larger than in silicon MOSFETs, it is possible to reach transit frequencies on the order of several tens of megahertz, but only by going to the nanoscale regime. Okay, so as long as the contact resistance is on the order, as long as the contact resistance is on the order of tens or hundreds of ohm centimeter, it will be necessary to make the transistors with nanoscale dimensions in order to achieve the kind of transit frequencies that we're aiming for. So thank you very much for your attention.
Thank you for this nice overview from an electrical engineer perspective. It was really interesting. So, questions?
Thank you, Hagen. Very nice talk and impressive transistors devices. I was wondering about that. Well, first, do you think there is room to improve this contact resistance via the contact doping the devices? And the second question, maybe also related. I think in your talk, you really never mentioned in particular charge trapping. And the charge traps, I think, is probably one of the nightmares in organic electronics to improve the performance. I don't know what's your opinion about that.
Okay, so I'll start with the contact doping. Contact doping.
You had that slide that you go past, but
contact doping. So it's almost so I cannot. Can I? No, I cannot click. Right? Okay, so I'll go to contact doping. So bear with me. Contact doping. Almost there. Almost there. Almost there. Almost there. Contact resistance. Contact resistance. Contact resistance. Comparison with inorganic, gate dielectric. Oh, where's contact doping? Oh, I lost it. No, there it is. Contact doping. Haha. So yeah, we tried contact doping. So yeah, absolutely. So in silicon MOSFETs and in basically any type of inorganic field effect transistor, the contact resistance is basically at the quantum limit. So as small as it can ever be. So that's about 1 milliohm centimeter. Only in organic transistors is the contact resistance still, even in the best organic transistors, orders of magnitude above the quantum limit. And the main reason is that we are not doping. Now, of course, we tried doping many years ago. And in fact, indeed, what we find is exactly what we expected. So this is the output curve of a nanoscale organic transistor without contact doping, and you see the signature of very large contact resistance here. And we can improve this contact resistance dramatically by introducing contact doping here, right? So the contact resistance drops by about a factor of 2 or 3 here, right? But that's not nearly enough, right? We're looking for orders of magnitude improvement, but that's a factor of 2. And there's a reason for that. And that is I think it's called doping, what's it called? Saturation. So no matter how many dopants we put into the organic semiconductor, only a small fraction of them actually gets ionized and contributes to a drop in resistance. And so there's a fundamental difference between introducing dopants in inorganic semiconductors, where they immediately contribute, where basically the contributions are 100%. Basically, every dopant we put in contributes 1 charge. In organics, that's not the case. And in fact, if we continue to put more dopants in, the efficiency will actually drop, as you can see in this graph, right? And so this is the main, this is a huge impediment to utilizing contact doping, which is why we basically stopped using contact doping at all, because it also has some detrimental effects. It lowers mobility and everything else, right? So we basically stopped contact doping. And so we're trying to use basically any number of other ideas. So we're trying to optimize the angle here of this edge angle here and make that shallow. We functionalize the surface of the contacts. We work very hard on maintaining a useful morphology of the organic semiconductor across this interface. So everything but contact doping. On charge trapping, yeah, well, that's obviously a huge problem, and that's something that I don't have nearly the time to go into here. So we try to minimize charge trapping by keeping materials and interfaces as clean as possible. So clean room, high vacuum deposition, purification of the materials. We're trying to avoid solvents, for example. You know, you introduce solvents, you get trapping, all those things. But yet, even so, we have grain boundaries, we have surface roughness, so there is charge trapping everywhere, obviously. So yeah, it's a huge problem, and it'll continue to be an uphill battle. Yeah. Oh, thanks for the question.
Okay, one more question.
Okay, thank you for the nice talk. I only wanted to ask you about the dielectric. You were using aluminum oxide,
right?
And then you prepare the aluminum and then you oxide it to the how much is the thickness of this aluminum, and then how do you control that thickness of 8 nanometer after you oxidize it?
Right. Okay. Plasma duration thickness. No, wait, this is titanium oxide. Plasma aluminum oxide thickness. Yeah, there it is. Okay, so yeah.
How reproducible is, because every time you oxidize, you don't know how exactly.
Well, actually, we do. So we we can measure it in situ, if that's what you mean. There's no in situ measurement. That's correct. So what we do is we have to calibrate. So we have basically so the main parameters for the oxidation process are the plasma power, which we can tune from anywhere from 10 watts to 300 watts, and the plasma duration, which we can tune from a few seconds to several minutes, as you can see here, right? So this is a stack where we've grown 5 different thicknesses of aluminum oxide simply by varying these 2 different parameters in different permutations here. And then this is what we get. We get thicknesses ranging from 4 nanometers to 7 nanometers. Okay, so we do have pretty direct control of that oxide thickness by setting these plasma oxidation parameters. Does that make sense?
Yeah, yeah. And then why do you choose this way of having aluminum oxide and not, for example, ALD or other thing?
The main reason is that we cannot pattern the dielectric if we deposit it by atomic layer deposition. When you deposit by atomic layer deposition, the aluminum oxide will go everywhere. Here, the oxidation, the advantage is that the aluminum oxide will only oxidize the aluminum gate electrodes, but it will not oxidize the rest of the substrate. And so we don't have to go back and pattern it. Oftentimes in microelectronics, the problem is not to deposit materials. The problem is to get rid of it where you don't need it. And this would be a huge problem if we were to deposit the oxide, for example, by atomic layer deposition. Of course, And there's a second reason, and that is the cleanliness of this interface. We just talked about trap states. And one important contributor to trap states is a hetero interface. But if we grow aluminum oxide on aluminum, it's a native oxide. And that will have the smallest possible interface trap density, as opposed to if we were to deposit aluminum oxide by ALD onto a different type of surface, then we would immediately have a hetero interface and thereby a larger trap state density. So those are the two reasons why we prefer the oxidation process over the deposition process.
Okay, thank you.
You're welcome.
Sorry, because we are coming a little bit late with the program. So I know that some of you have more questions, and Hagen has to leave now and to take the taxi. So
Thank you very much.
Thank you. So let's continue with the session of this afternoon. So now Weronika, that is here at ICMAB, doing the postdoc in the group of Jan. So she will speak about a little bit about the Spintronics. So the floor is yours.
Well, so hello everyone. My name is Weronika Iga Janus, and it was already mentioned. I work here in ICMAB in Mulfolk's group under supervision of Jan Onurafci. And today I will briefly introduce you our recent research on rare earth iron garnets for spintronic application. So as we all aware, due to the increasing demand for data processing and storage, conventional electronics is facing some challenges. And an alternative solution for that could be spintronics, which in addition to the to the current charge, it also mainly use spin degree of freedom in order to store and also process information. And what is particularly interesting about spintronics is that it's very versatile because depending on the heterostructure that we engineer and the devices that we design and also material that we choose, we can really choose different paths in order to achieve this main goal. So speaking about the material choices, one of the very promising platforms are rare earth iron garnets. So those materials are quite complicated. They have quite complicated crystal structure and also magnetic structure because they have like 3 magnetic sublattices that are all coupled with each other, and their magnetization contributes to the net magnetization of those materials. Those materials are ferromagnetic insulators, and particularly interesting is their unique set of properties because they exhibit, their magnetic properties are easy to tune, they have perpendicular magnetic anisotropy, low damping, etc. And those properties can be very beneficial for spintronic application. However, if we want to use those materials in spintronics, we have to know these 2 things. So we have to be able to electrically control and also detect the magnetic states. So far, people mostly use this method of detection, spin magnetoresistance detection. However, it's very limited because the signals here are pretty low. And also, in order to detect the signal, we need this 4-terminal device, which is quite impractical from the technological point of view. So our first question was if we can use another effect to read the state of a ferromagnetic insulator. So, for example, in metallic system, we can use this giant magnetoresistance effect. And this effect can be read for such as spin wave structures where we have 2 magnetic layers separated by non-magnetic spacer. And the resistance of such a heterostructure depends on the relative orientation between these 2 magnetization. And very importantly, we can read the signal in a current in-plane geometry in simple 2-terminal devices. So we try to implement this solution into the spin wave where the information is stored in a ferromagnetic insulating garnet. And successfully, we were able to observe the signal. However, it was still quite low. So in the next step, we wanted to somehow increase this signal. And here we implement some interface engineering. So we insert this thin ferromagnetic layer between our garnet and a spacer in the spin valve. And for this new heterostructure, we not only were able to still observe magnetoresistance signal, but also by carefully choosing the thickness of this ferromagnetic layer, we were able to increase the signal by more than 2 orders of magnitude compared to the structure without this additional layer. So after that, we wanted to check what is behind this increase. So we performed some additional electrical measurements and also some synchrotron measurements at Alba synchrotron. And with this, we found that in such a bilayer, we have some interfacial coupling between this perpendicular magnetic anisotropy in a garnet and magnetization in a ferromagnetic layer. And this coupling caused the magnetization of the ferromagnetic layer to tilt away from the surface, meaning that we have some small out-of-plane component of the magnetization. And then if we look at the tilting angle behavior as a function of the thickness of this layer, and we compare with magnetoresistance signal, we can see that this increase in magnetoresistance is directly correlated with this perpendicular component of ferromagnet magnetization. So this actually motivates us to explore more the possibility behind the couplings between the garnet and ferromagnet. And in the next research, we focus on this simple bilayer system, where we have terbium iron garnet with perpendicular magnetic anisotropy and ferromagnetic layer, this time cobalt iron boron, with uniaxial in-plane anisotropy. And for this new system, we, in addition to the collinear coupling that we also explored for the previous system, we also found some chiral coupling between the two layers. And this chiral coupling is related with interlayer Dioshensky-Moiré interaction. And for now, the most important thing is that about this coupling is that it favors a unique sense of relative rotation between the two magnetization. And this simply means that with this chiral coupling, we can have like different states in our samples, favored and unfavored, meaning that there are some preferential relative orientation of the magnetizations between the two layers. So we performed some Moog measurements as a function of temperature, and we found something really interesting. So we found that if we measure our system at room temperature, and we fix the direction of the magnetization of the in-plane layer, we can actually stabilize the out-of-plane layer either up or down, meaning that we can achieve both of the states, favored and also unfavored. However, if we increase the temperature, there is only one state possible, with the in-plane layer determining the direction of this out-of-plane layer. So simply, it means that if we set the unfavored state at low temperature, we increase the temperature, the magnetization of the out-of-plane layer will rotate in order to achieve this favored state. And this can be also done with electrical currents. So here we have some Moog images in which we can see that if we set this unfavored state at room temperature, we pass current through the device. It doesn't matter the polarity of the current because our goal is just to induce Joule heating. Then with this, we can switch the magnetization of this out-of-plane layer. And then if we want to switch again, we have to also rotate this magnetization of the in-plane layer because this is the one that determines the state. And as you can see from these figures, this switching is quite, is deterministic and is also reproducible over multiple switching cycles. So this brought me to the end of this presentation. Thank you very much for your attention. And I will leave these conclusion slides here. If you have any question, I will be happy to answer now, or later I will be around. Thank you.
Well, thank you. Thanks for being so right in time, because even I was not expecting. Any question?
Can you explain me, because I did not understand why one state is, so the what is unfavorable?
Yes.
Because I see it like completely equivalent. What is that makes one?
Yeah. Okay. Let me go. I have some backup slides, so maybe it will be better here. Okay. So this chiral coupling makes this chiral coupling. How to say? So thanks to this chiral coupling in our sample, we have some internal fields that causes that the in-plane layer acts on the out-of-plane layer, and also out-of-plane layer acts on the in-plane layer. So those fields can either hinder or assist the switching. And well, if you look at the loop, it's shifted, right? Mm-hmm. So due to this shift, since now I should go back to here. So then also the loop here is shifted, but if we increase the temperature, you can see that the entire loop is shifted. So this means that this internal field in our sample that is due to the chiral coupling between the two layers, like suppress the coercivity of our loop. And this is why the only one state is possible at this temperature. Okay. I hope that, yeah.
Okay. So let's try to move on. Yeah, okay. So thanks again, Weronika, for this nice thing. So let's move to the next talk. Yeah. Eric Langenberg. So he's coming from University of Barcelona, and he did the PhD under the supervision of Josep Fontcuberta, Manuel Varela, many years ago. Well, many years. Some years ago. So thanks. The floor is yours.
Okay. Thank you. Can you hear me, all of you? Okay. So, well, nice I'm glad to be here again. So in the ICMAB, and I'm going to talk a little bit. It's going to be different from magnetism and electronics. So the previous talk, it was magnetism. The previous talk was more electronics. Here, we're going to talk about thermal memory. So thermal current, but actually with the similar goals to have like a processing, storage information, we said with electrons, or electronics, or with magnetic and spintronics. We're trying to make it with a thermal current, which is kind of a little different. And just for a kind of introduction, what we like to have as a thermal memory is a material, an active thermal barrier that can change the thermal conductivity with an electric field, and to make it like a high thermal conductivity or low thermal conductivity that allows the thermal current to go through in the on state, or inhibiting the thermal current through in the off state, and have it like a bit 1 or 0 with thermal currents. Okay. And then why thermal memories? So when we can build like an equivalent circuit, like an electronic circuit, but instead of electrical current, thermal currents, we can use these as a thermal regulators for instance, in electronic devices, the endurance and the fatigue is affected by the thermal fluctuations. If we can have a thermal regulator that can change or dissipate the thermal energy more efficiently, it's going to be useful in electronics. But as I said before, it can also be used to build up a new technology, and instead of storing information electrically, storing thermally, and having a bit 1, a bit 2, a bit 0, a bit 1, just for having high or low thermal conductivity, passing or not passing thermal currents. And then the question is how to modify the thermal conductivity in a solid state material. Okay, basically we have like 3 main ways to do it. Basically, one is interfaces scattering phonons, and so if you put more and more interfaces, or the density of interfaces is larger, then you're going to reduce the thermal conductivity just because you're going to have more scattering phonon centers. Okay, the other way, this is a super lattice. The other way is introducing defects like vacancies. Okay, if you increase the density of defects, we're going to have scattering more phonons, and the thermal conductivity is going to decrease when you're increasing the number of defects. I think the slides are going to move because of the transition of Mac and Windows, I guess. But let's hope it's going to be fine. Another way is also with the phase transition. If the 2 phases, they have different thermal conductivities, if you change from one phase to another phase, then you're going to have a different thermal conductivity and thermal current. So, but then the question is how to make them electrically active. So how can we change that with an electric field? That is because all these materials are fixed or in a constraint with a temperature in the vanadium oxide. So how can we make them like electrically active? And one way is using an ferroelectric material, because ferroelectric materials, they have intrinsic interfaces, that domain walls that can be moved with an electric field. So we can actually polarize an electric field, ferroelectric, remove all the domain walls, have a single domain, and then a single domain with no interfaces, the thermal conductivity is going to be high. And with a large number of the interfaces at the coercive field, it's going to be low thermal conductivity. And then we can change that with an electric field. And that's actually, years ago, we proved that in lead titanate, the density of domain walls matter. So I modified the density of domain walls in the lead titanate doing epitaxial strain, and changing the strain, you can change the density of the domain walls in your material. And then compared to a single domain in lead titanate, the thermal conductivity decreased significantly as we increase the density of domain walls. So domain walls, they scatter phonons. But the question is, how can we change them electrically? With a PFM, I can write the lead titanate films, and we can put domains and domain walls easily, but locally. So if we want to do it at room temperature in lead titanate film, at 5 nanometers of a lead titanate film, I haven't seen very few reports of a polarization hysteresis loop in a lead titanate film epitaxial of 5 nanometers. So they're basically quite leaky. So it's very difficult to do that. Okay? And that's why we moved to another material. This is hafnium zirconium oxide. So this is actually a report by here in the ICMAB by Fina and Francis Sanchez of hafnium oxide. And they can be very, very, very insulating even at 5 nanometers film. So that's why we moved to hafnium oxide to have the possibility to do all this electrical field and changing the domain walls in a ferroelectric material, very, very thin. And then, so we can actually stabilize this ferroelectric phase epitaxially, and we did that in using a 111 oriented YSZ substrate, and then we can stabilize the polar phase. We proved it a few years ago. And that is why we use this material as a flagship to check how the domain walls can change the thermal conductivity. And then we grow the sample on YSZ. So it was like epitaxial and polar. And we have the polar phase, the orthonormal phase, the polar phase. Okay, and then that was our test sample. And then we measure the thermal conductivity with an optical technique, a pump probe technique, which is frequency domain thermal reflectance. And we deposit the gold on top of it, and we measure the thermal conductivity of the whole structure and computed the thermal conductivity of our hafnium zirconium oxide. Okay? And then this is actually the result. So here we have the thermal conductivity as a function of the electric field. And it's actually the first hysteresis loop that we have got. Actually, I haven't seen anyone reported, of the thermal conductivity versus electric field. So this is the dark blue dot is going from negative electric field to positive electric field, and the light blue dots are the way around. Okay? So this is theoretical. This means that allows defining two thermal states, high and low thermal conductivity, on and off. And we also measure the polarization of this ferroelectric sample, and these are actually where the coercive fields of the polarization. This is actually the current versus electric field, and the coercive field in the polarization hysteresis loop coincides with the coercive fields of the thermal conductivity versus the electric field, which is something is related with the polarization and the thermal conductivity. And then at room temperature, because all these measures were at 200 degrees, at room temperature, the two states, the thermal conductivity, the on and the off state, remains stable at least 4 days. Okay. But then the question is what is the mechanism behind that? Because I was telling you before that there was domain walls that related with these scattering phonons, domain walls, high density domain walls, and low thermal conductivity, no domain walls, high thermal conductivity. But if it were like this, our thermal response should be something like this. Okay, this is a very naive draw, but the thing is, the minimum in the thermal conductivity should be at the coercive fields, because at the coercive fields is where we have the highest density of domain walls. And we don't have this picture. Our picture is an hysteresis loop resembling a polarization versus electric field hysteresis loop, and we don't have that picture here. So domain walls may affect in the thermal conductivity in our hafnium zirconium oxide, probably, but not sufficiently. Or at least it's not the main driving actor controlling the thermal response of our hafnium zirconium oxide. Our second guess was, are we inducing with an electric field a change of phase? It could be, because this material is orthorhombic, but it's actually metastable. The stable phase is monoclinic. Might we inducing a phase transition with an electric field? Could be. But the thing is, both states, in the on state and the off state, the film remains orthorhombic. So we are not inducing any phase transition in our films. So what remains? Well, this is not the mechanism. Then the thing is our theory is that we are dragging and depleting oxygen vacancies within our electric field. So when we apply a very sufficiently large negative and applied electric field from top of the gold, we are dragging the oxygen vacancies of the YSZ to the hafnium zirconium oxide, and these vacancies, the oxygen vacancies, are going to do this scatter. So they're going to scatter phonons. We're going to reduce the thermal conductivity, and that's why we have this low thermal conductivity here. Then, if we go to 0, just because we have polarized our hafnium zirconium oxide this way, because of the electric field, this polarization inhibits the oxygen vacancies to come back to the YSZ. So oxygen vacancy basically stays there, even though the electric field is 0. That's why we have this non-volatility of the state. Then we increase the voltage to the positive, sufficiently higher than the coercive field. So we switch the polarization as well. And then we we push these vacancies to the YSZ again. And then the thermal conductivity is going to be high because we have removed our vacancies. And then, again, as before, well, we can go here. Then because when we go to 0, just because we have depolarization, the vacancies are not allowed to come back to the YSZ, to the hafnium oxide. And that's why the thermal conductivity is going to be high. So we are finished, right? Okay. So actually, these are going to be the summaries, these conclusions, okay? So we have opening a new avenue, because it is a new mechanism to tune the thermal conductivity of material using the coupling of polarization and oxygen vacancy migration, which can be used not only for hafnium zirconium oxide, but other hafnium-based ferroelectric films like lanthanum-doped hafnium oxide, yttrium hafnium oxide, and let's see in the next years how it's going. Okay, thank you for your attention.
Thank you, Eric. Maybe we have time for one short.
Thank you very much. Nice talk. I was wondering if you have any experimental proof for the presence of those vacancies when
That's a very nice question. Actually, we couldn't see. We wanted to see in the scattering distribution electron microscopy, but the vacancy concentration, actually, if you could the backside slide. So the number of vacancies are so low, the concentration is like 3 vacancies per 100 unit cells is sufficient to reproduce the results in the theoretical calculations. No. So the thing is, the concentration is too low to be seen the scattering distribution electron microscopy, or at least we couldn't see it. So, but the theoretical calculations, actually, this is the experimental results. It was a theory here in the group that we computed the number of vacancies that can reproduce the results of thermal conductivity of our hafnium zirconium oxide, and it was quite low. The concentration is enough to scatter phonons and to reduce the thermal conductivity. We couldn't see it in scattering distribution electron microscopy. You're welcome.
Okay, so we have to move to the last speaker. So thank you, Eric. So thanks Mónica for coming here. So she's working she's an early stage researcher at ICMAB, let's say.
Early stage?
Early stage. At least at ICMAB, no? At the Institute of Nanociencia Materiales of of Aragon. And thanks for being here. And the floor is yours. So.
Okay, great. So thank you very much for inviting me to this 40 years anniversary of ICMAB. It's really a pleasure because I'm an alumni from ICMAB. Last time I was in this stage right here, it was my PhD defense, so many years ago. So it's very, very nice to be back, and particularly because, as you said, it's the 40th anniversary not only of ICMAB, but also of all the material science institutes of Spain. And now I have recently had a new position at INMA in Zaragoza, so we are also celebrating our 40th anniversary. So this is the last time I was in the States. That was 19 years ago, a very long time ago. So just before I go into the science, for those who know me, I've seen lots of faces here today. It's been very nice because some of you I've seen in conferences, but some of you I hadn't seen for a long time. So I'll explain you a bit of my journey from ICMAB to INMA, my scientific journey, and then I will really go into science. So as I just said, I did my PhD between 2003 and 2007 here. So I was not at the beginning as the people who were talking this morning, but I was at the half time of this, like half time of ICMAB. And my PhD supervisors who were in the previous slide were Jose Santiso and Gemma Garcia. And Jose Santiso moved to ICN2, which is just here. So when he moved, I did a few months of postdoc with him. So I moved there and I used a bit the post-laser deposition technique there. From there, I moved to Germany for 1 year, in which I was working on also perovskite materials, but more for membrane applications. Then from there to London, I was there at Imperial College. I was doing lots of low energy ion scattering, secondary ion mass spectrometry, oxygen diffusion measurements. And my last place before coming back was in Grenoble. So when I arrived there, I was in a collaboration with IDEC from here, but finally at some stage I got my own projects. This was when I started with my own research line at LMGP laboratory. After this, I finally became a research scientist. So for me, it was not so easy as for Amparo, who was telling this morning that just after the PhD, she had a position. Well, I moved a lot before having my research scientist position. And then I was promoted to research director in the same lab. And finally, very recently, so as for 2026, now I'm a research professor at INMA in Zaragoza, so very close to here. So it's very nice to be back in Spain and very close to ICMAB. It's a very fast train ride, so I think you'll see me more often now that I'm close. So what have I been doing? What is my research line right now and during these years? So I basically worked with thin film deposition, so mainly metal-organic chemical vapor deposition and post-laser deposition. I've been very interested in the ionic and electronic transport properties of these thin film materials. And in the last years, I've also become interested of integrating them in real devices. So the part I will talk about today is memory-resistive devices for neuromorphic computing, but there's another research line I've had in parallel, and I will continue now at INMA, which is for solid oxide fuel cells and electrolyzers. Okay, and this is how I do things in the group, or we do things, because it's not me alone. So I look into materials which have point defects, normally oxygen vacancies, oxygen interstitials, which allow oxygen to diffuse into them. And the families I've been looking at are mainly perovskites, perovskite-related materials like lanthanum nickelate or fluoride materials. Then I deposit them by MOCVD or PLD, thin films. And what is very interesting is that depending on what the application is, if we want to do any fundamental studies, we might be interested in epitaxial films. We might be interested in dense films for real applications for memories, or in very porous films with very high surface active area for electrodes for solid oxide fuel cells. So we tune the materials properties, then we do advanced characterization. I will show a bit of that today, at least of the resistive switching parts, but we've also developed an isotope exchange Raman spectroscopy technique in the last years. And then finally, we integrate them in devices. So they can be memory-resistive devices or reversible solid oxide cells. And then, of course, this is a loop. Once these work better well, we feed it back to the material selection and optimization. So this is what we work on. And now, really coming into the science of this talk, I would like to start by explaining you what are valence change memories and why we use them for artificial synapse applications. So all of you know that the computing power and demands have increased hugely. Now that artificial intelligence is here. So about 2012, it's rarely been an exponential growth. And the cost is enormous, and it's becoming enormous. And we have to try to find a better way of reducing this energy. So one of the proposed ways is to use these neuromorphic computing systems where the memory and the computation is stored in the same location. And we try to mimic what the human brain does. It's super efficient. We only need 20 watts for the human brain to work. So we try to mimic what biological synapses do in the brain. And for this, we use what are memory-resistive devices or resistive switching memories. So they're very simple, okay? We have two electrodes, and between that, a material that it's typically insulating, or sometimes it's mixed or semiconducting, sorry. Okay. And how do we do this resistive switching effect? So we apply a voltage. We have if we start with an insulating material, we have a high resistance at the beginning. We would be in this red line here, okay? And then we apply to one of the electrodes is grounded, and the other one we apply a voltage. And when the voltage is high enough, we change the material state to low resistance state. And then we will stay in this low resistance state until a high enough voltage is applied to the opposite direction. And then we would be, by applying a positive or negative voltage, we could change the resistance state from high to low resistance. Okay. What else can we do? And some of these devices are only binary, and we only have two states. But what is very interesting for neuromorphic computing is to have lots of intermediate states, as we're seeing here in this analog type computing. So we can apply pulses to the device, and it will change from one resistance state to the other, but with lots of multi-level states. What do we need? We need some specifics, metrics for these devices for neuromorphic computing. So what do we need? A memory window, so the difference between the high and the low resistance state, as large as possible. About 10 is large enough. What else? Low variability. This refers cycle to cycle in the same device or device to device. Strong endurance. So it means that we can cycle them for more than 10 to the 5 times, lots of cycles, and it has to behave the same. Long retention, very fast switching speed, so less than 10 nanoseconds, and that we can do this potentiation depression with lots of states. And finally, we wanted to reduce the energy, so we have to, each of these operations should have a very low energy consumption. Okay, so this is our ideal device. Then it's very difficult to reach all these characteristics. So there's mainly two types of valence change memories, resistive switching devices, two different mechanisms. The most common one in literature and in industrial applications is the filamentary switching. This means that when the device is in the off state, high resistance, and to make it work, first you have to apply a very high voltage. So here we see what is called the forming voltage. And what normally we think it's formed here is a filament of oxygen vacancies, which connects one electrode with the other. It's very fast, these type of devices, but it has some drawbacks. So you need this high energy for the forming. you have a very abrupt set and reset between these two states and a high variability. Second type of devices, interfacial type switching. So here we do not create a filament. What we do is to move the oxygen vacancies close or far or more or less towards one of the interfaces. And then normally these memories operate from the beginning. We don't need this forming steps. We have gradual switching, so we can have lots of different states by using different set voltages. Normally they have lower variability, but the problem is that they are relatively slow compared to the other type of devices. So these are the state of the art, as I've said, in the literature, in the industry. Most people use N-type conducting materials and this filament type. But what we did, and we started this work already many years ago, is a totally different approach. So we chose this lanthanum nickelate material, which is oxygen rich. So instead of having oxygen vacancies for the oxygen diffusion, we have oxygen interstitials, and it's a P-type conductor. Okay, and now I will move to really, after this introduction, show you some of the most important results we've obtained during these years. So why did we choose lanthanum nickelate? Well, first it was the material of my PhD thesis, so I knew it well. But apart from that, what is good from it? So we can adapt to lots of different oxygen stoichiometry. So we can have, with having the same structure without breaking it, we can have lots of different oxygen contents between 0 and 0.2. So it can transport oxygen because it has a high diffusivity. It's formed by a layer structure with perovskite and rock salt layers. And in this rock salt, we have the interstitials that can move easily within the structure. And it's a P-type conductor. This means that if I put in oxygen into my structure, I will change the whole concentration. And with this, I will change the conductivity of the material, which is what I'm looking for. So we did it in Grenoble, in the lab where I used to work at LMGP, and we were using post-injection metal organic chemical vapor deposition. So we mix the precursors in a solution. We evaporate them by flash evaporation with an injection valve to the evaporation zone. They're carried by a gas flow, and they go to the reaction zone where they are deposited, and we have the film growth. Okay, so now these are the first, when we started working with these materials, we started working with epitaxial films. So we grew them on single crystal substrates. And then what we put was the 2 electrodes on the top of our material. And we started with platinum and titanium. So we already had a nice analog type switching here. But after that, if we want to go really towards industrial applications, it's not very reasonable to work with such large distances between electrodes. And we moved to this vertical configuration. So here we have a common platinum electrode on our sample, our lanthanum nickelate, and titanium on the top. This was the first PhD student here. That was the second. So Klaus-Jan Maas was the first PhD student on this work. Kan was the second PhD student working on this, and he used, at the beginning, titanium as top electrodes. We also obtained some nice memory resistive switching curves. You see here the high stereicities, the 2 states. However, it was not very reproducible. We believe that because this titanium gets oxidized at the interface, but we were not able to do it in a reproducible way. So in the second part of his PhD, he moved to titanium nitride. And since we moved to titanium nitride, we really have very reproducible results for these type of devices. So now I'm not going to explain the first works. I'm just going to talk about the titanium nitride electrodes. But again, we started with one PhD student, Kan, and then we continued with Alexandra. So there's lots of results here. First, I will show you the analog resistive switching characteristics of the films, then how we can play with these characteristics by changing the oxygen content of the synaptic properties. Later, we moved on, and we moved from these type of devices to cross-point devices. And finally, we did a deep investigation about the resistive switching mechanism by some advanced characterization. Okay. So these are our thin films. We deposit on platinum substrates. There's no epitaxial relationship, so we have a polycrystalline thin films, which we see here by SEM. The roughness is about 3.4 nanometers. And we have the expected phases, polycrystalline peaks by XRD. Then we deposit titanium nitride in the clean room by reactive sputtering with some masks to obtain the devices here. And what we already observed, so then we characterize in depth these devices, and we already observed that just because of the titanium nitride deposition, we had some oxygen migration to that interface. So lanthanum nickelate gets reduced and titanium nitride gets oxidized. And this is very important for the switching behavior of our devices. We also confirmed this by some synchrotron measurements at the nickel K edge by X-ray absorption near edge spectroscopy. So we measured in the same sample some regions where we had an electrode and some regions where we did not have an electrode. And we see that the nickel K edge shifts. So below the electrode, we have more nickel 2+, let's say, and we have more nickel 3+ in the electrode free region. So we see that nickel is reduced by the deposition below the titanium electrode. Okay, then we try the switching to switch these devices as we want them for resistive switching memories, and we could see that we could play in different regimes. So if we play with a low voltage range, positive and negative, ±2 volts, we can show this relatively small on-off ratio of 5. And if we plot the resistance versus the electrode area, we see that we have a slope about -1. And this is telling us that it's the whole area that's switching. So we have an interface type switching in this case. What happens if in the same device we apply a higher voltage? So we do what we call soft forming. So we create something, a filament in our device, and then we can have a much larger, so we pass from 5 to 50 in the high to low resistance ratio. And now we do not have an area dependence anymore. All the devices, as it's a filament that is connecting and connecting, the high and low resistance states is independent of the electrode side. So now, as I told you, we want some switching characteristics. So we have to fully characterize all the electrical properties of our devices. So we have a very nice cycle-to-cycle variability. The device-to-device is a bit worse. We can still distinguish clearly two different states, but there's some variability. And then, of course, we saw that we retain. So these memories are non-volatile. This means they retain their state after a long time at 85 degrees. And we have a high endurance. We can switch them many, many times, 10 to the 5 times here, without losing their switching characteristics. So now I'm going to move to the next part. So I'm going to explain, as I told you, we can play with the oxygen stoichiometry in these films. So we wanted to see what happened if we change. If we do an argon anneal, we will reduce the oxygen content. If we do an oxygen anneal, we will increase the oxygen content of these devices. So that's what we did. Then we took them to the synchrotron to measure the nickel K edge. And we saw that the films, as expected, changed their oxidation state by oxygen anneal or argon anneal. Then we deposit, We see the same by XRD. So when you introduce oxygen, the C parameter expands and the AB plane decreases, and exactly as we expected. So then we checked by EOS what is happening exactly below. Well, okay, these are annealed samples. We put the titanium nitride on top. And as I said before, this titanium nitride tends to oxidize the sample. So there's oxygen, and this we proved by EOS with César Magén from INMA that the oxygen concentration changes from the bottom to the top electrode. And we can see this by the appearance of this pre-peak and the lower intensity at the top compared to the bottom. So we have a gradient in oxygen concentration through our film. And that is what is shown here, where we did the oxygen gradient as a function of the distance. Okay. So now we have the two types of devices, argon annealed, oxygen annealed. So we will start with this one, is the argon annealed, yes. Yes, argon annealed, sorry, back. No, I'm going forth, sorry, back is here. Okay, argon annealed, yeah, it's written here. So now we have less oxygen in our material, and we try to do the switching. And what we obtain is a filamentary switching. So we have, as I showed before, for the pristine devices, we have a forming step, and we have two high and low resistance states that are the same independent of the area. What happened for the oxygen annealed devices? Sorry, now I went back instead of forth. Okay. The devices behave very differently if we did an oxygen anneal. We have a higher concentration of oxygen. The material is more conductive. And instead of having this filamentary type switching, we have interface type switching that we can see by no big jump in the curves and by this area dependence of the resistance. Then we did all these steps of what is called potentiation and depression curves. So you apply a number of positive pulses and then negative pulses, and you measure each resistance states that you obtain, and you repeat it many times to see if it's reproducible. So this is what we obtain. We have to play a lot with the conditions of the pulses, the length of the pulse, the duration of the pulse, and these were the optimized conditions for the argon annealed samples, and these are the optimized conditions for the oxygen annealed samples. So when we couldn't get the filamentary switching, we have a lower window, slower switching kinetics, increase in the voltage amplitude, and higher energy consumption. So these ones, the argon annealed, clearly worked much better. So now, yes, what we've been doing up to now is working in this type of devices. We have a plain sheet platinum electrode that we ground, and we have each of these electrodes that we go individually to test one by one to do all our statistics. However, is not really how a real device will work. In a real device, what you will have is that the bottom electrode is also patterned. Here we were really limited for the downscaling to the size of our tip that we could contact. And you can damage the electrode, you can scratch it, you can really touch the film sometimes. So we wanted to do better, and to do better, what we did is to do these cross point electrodes. So then we contact far from the electrode, we do not damage it, and we're really measuring smaller sizes of devices here. We could go really downscaling. This is our design layout. And these are the characteristics that we obtain. So there's also, in the laboratories, when we study resistive switching, we have some characteristics that sometimes are not really what a device in the real industry will work. So we really have to do this exercise of downscaling and seeing if the performance is really the same. So we saw these are the ones in yellow are our new crosspoint devices, we saw that we had to apply a higher forming voltage to make these devices work, and that there was a serious resistance that had an impact in the switching curves. However, we had very nice analog properties. So we had a more gradual reset in the crosspoints array, crosspoints devices compared to the other devices. And finally, we can say that we successfully downscaled to 5 by 5 micrometers. So we reduced and we could operate them very nicely. So these are the characteristics. We have the forming, the set, the resets, the cycling. We did all these measurements of cycle-to-cycle variability, endurance, retention, long-term potentiation depression. And what I want to show you is, I told you before what we want for a real device. Where are we now with our optimized devices? So we've achieved a very good window, very good endurance. We have very fast switching speed for the depression, but not for the potentiation. We have lots of levels. We have a very low energy consumption. So there's only the retention that we still have to improve, and the variability, which still can be improved. Okay, and now I'm gonna pass to the last part of the talk, when I'm gonna explain you how we've combined all these different advanced characterization techniques to try to understand what is really happening inside our device when we're doing the switching. So we combine operand access with scanning thermal microscopy, well, TM, and then some conduction mechanism analysis. So here, this is at the ESRF synchrotron at ID12 beamline. So we did the experiments as in our lab in the same conditions, because we just placed with the sample here with the electrodes. We were biasing in the same way and measuring at the same time. So if you have done these type of measurements, you know probably that it takes quite a long time to have a good spectra for example, your nickel or whatever edge. So maybe they're 20 minutes measurements, and that was not compatible with our operando measurements where things switch fast. So what did we do? What we did is to measure well, first we did the whole measurement, but then we did the first derivative and found what is the edge point. And then we were just looking at this edge point while we were cycling with time. So we know that if the edge moves to the right, we will have oxidized the nickel. So really the intensity will decrease. And if the intensity in this point increases, it means that we reduce nickel. So it was a way of trying to do switching measurements that worked at the end very well after lots of trials. So here we have, for example, 10 cycles where we have these IV samples, and there we're measuring the absorption intensity. So here we're in the high resistance state, and then we see a change, and here we're in the low resistance state. So then intensity really increased and decreased, and we can directly estimate the nickel oxidation state from the nickel position. And at the end, we can relate to what's happening in our sample. Okay, so what happens when I apply a negative bias and I'm doing the set? So oxygen is coming into my sample. And we really prove this vacancy change mechanism because we measured experimentally that the nickel oxidation state was changing, and the opposite is happening. So when we apply, as could be expected by a positive potential, the oxygen comes out of the lanthanum nickelate and into the interlayer here. Okay, so yes, we prove this valence change measuring by continuously measuring just at this fixed energy. What did we've been done very recently to try to, lots of people talk about filaments in these type of devices, but most of the people do not see or do not show the filaments because it's very difficult to find. But what did we observe? These are our cross-point devices. This is before any switching, before any forming, and what happens after forming, after applying the first high voltage. We see something, this is an SEM image. The color has changed here. What happened? We can focus on that region. It's about 600 nanometers, the spread region here, circular feature. So we believe that probably we have a filament here, but just by this, we cannot say for sure. So this was done in collaboration with this INL Institute in Lyon, as I said, during the last months now, and they use a technique that is called scanning thermal microscopy. So it's like an AFM tip, let's say, but of palladium, and they measure the thermal, the resistance, and that gives them information about the temperature. So what we did is that we could apply a voltage and at the same time measure the temperature changes in our sample. This is what we saw by SEM, this white part. By AFM, we see that it has a morphology, so it has a bump. And here is where we really see the filaments. We really see that is the region that is heating when we're doing the measurements. So really it's localized Joule heating, so it confirms us the presence of this conducting filament. Now we took one of these samples, one of these cross points, and we did a fib lamella here. This was done in collaboration with César Hagen also. And we can see in the lamella, as it was very long, this is the filament region, and here is a pristine region, and we can observe it in the same experiment. And here is what we see. So that is the pristine region. Each element we can see is where it should be. Nothing has moved in this region. But now what happens if we compare with the conductive filament region, which is this part here? So here we can see changes in the nickel depletion. So nickel is not here anymore in this top part region where it was before, in the top of the nickelate. And here we can find some titanium oxide formation in the top of the electrode surface. Okay, so now we have some chemical information, and the last piece that we want to put together in this puzzle is the conduction mechanism. So we did this analysis of the conduction mechanism, first of the switching curves that we're seeing here, and we see that both for the high and low resistance state, in the positive and in the negative polarity, we can see the space charge limited current conduction with the different slopes that correspond to the ohmic region, the trap field limit, space charge conduction, and the trap. What we also tried to do is to analyze not when it's switching, but really in the high and in the low resistance state. So we measured at these different temperatures. We did between 295 and 395 degrees, and we did this smaller IV curves, but it means you're in the same state, you're not changing the state, you're in the high or in the low state. And we saw that for the high resistance state, there's a strong temperature dependence, which we think is associated to the Schottky barrier contribution, while for the low resistance state, there's a very weak temperature dependence. So we think this Schottky barrier has collapsed. Okay, now we did these plots of the current, that would be the same as conductivity versus the inverse of the temperature. For the different points we have measured at different voltages. And from here, we can extract an activation energy. So we have the activation energy from the low and from the high resistance state. From the low resistance state, we could extrapolate to the activation energy at 0 volts. And we can compare with the literature for lanthanum nickelate. That is our material, switching material in principle. And we see it has a very similar activation energy. So we really believe that for the low resistance states, the lanthanum nickelate is dominating the conductivity measurements, while for the high resistance states, where you have a much higher activation energy, there's a very strong contribution of this titanium oxynitride interlayer. Okay, so now I'm putting the 4 pieces of information together that we've got from the characterization, and we tried to develop a simplified model to see what is happening in our devices when we're doing the switching. So we believe that when we deposit titanium nitride, well, we believe and have observed that there's the titanium oxynitride layer that has formed and a gradient in the oxygen stoichiometry. If we only apply low voltage below the forming voltage, what we believe is happening as we have an oxygen exchange between the oxynitride and the lanthanum nickelate layer, and the hysteresis is due to the change in hole concentration of the lanthanum nickelate. That is in the first switching regime. When we go to the forming, what happens? We believe that there's a conductive filament forming in the titanium oxynitride layer. And then when we do the switching, this filament would be connecting and disconnecting. So we have in reality a behavior that is not only filamentary, not only interfacial, because we have in the whole surface oxygen that is going in and out between these 2 layers, but at the same time, there's a conductive filament that is connecting and disconnecting. And with this, I would like to pass to the conclusions. So just as a summary, take-home messages, we optimized very nice titanium nitride, lanthanum nickelate, platinum memristive devices with very high or quite good performance metrics and analogous switching. We could control the different type of switching by changing the oxygen stoichiometry. We could transfer to cross-point architecture. Then we've done lots of characterization, but one original operando sense methodology to really measure these changes. And we elucidated the mechanism of the switching by combining all this. And with this, I would like to thank mainly the people who, so most of the results I have shown are from the thesis of Khan and of Alexandra Goroleva. All these people were involved at LMGP in our laboratory. And then, of course, I've shown you lots of techniques. So obviously, there were lots of laboratories who were involved in these measurements, both in France, in Grenoble, Timaleti, SRF, and INL in Lyon. LTM is also in Grenoble, and INMA here in Zaragoza. I would like to, of course, thank the funding, and I would like to thank you very much for your attention.
Time for one question.
Yeah, thank you very much. I was curious about your titanium oxynitride composition.
Yes.
So do you have an idea of the nitrogen to oxygen ratio? And also, is this really, you have really an additional interface forming? Because in your cartoon, you had titanium nitride and then titanium oxynitride, or else you have a single phase with some sort of solid solution and gradient.
It's more a solid solution.
So it's not really.
No, it's not. Okay, that's a cartoon.
Yeah.
But it's It's really a gradient in the oxygen concentration. So for sure, we've measured at the interface that it's not pure titanium nitride. There's some oxygen, but there's not two-phase separation.
You know how rich how high can be the oxygen to nitrogen ratio?
No, I don't know. We did recently some more, Cesar did a couple of weeks ago some more EELS measurements. So from there, we probably will have a better quantification. I don't know the number right now.
Thanks, Mónica. Very interesting. My question is, do you know what is the role or how relevant are the grain boundaries of the lanthanum nickelate on these processes? So if you would have epitaxial films, would you expect the same?
I would expect different. I don't have an experiment where I have done with or without grain boundaries, because when we did epitaxial, we did 2 top electrodes, and when we did polycrystalline, we did top bottom. So I cannot, but I would expect there to be a difference. The grain boundaries can be really hot spots for filament formation, for example, or for defects, and normally the oxygen conduction will be different there. So for sure they will play a role, but I don't have an experiment where I can tell you exactly.
Thank you.
Thank you, Mónica. One question. Thank you, Ignacio. One question about the electrode, the titanium nitride.
Yeah.
Maybe you mentioned it, but why this electrode or not using another one?
So I want an electrode that will oxidize. So it's an oxidizable electrode from which I kind of can exchange oxygen in and out of the structure. So that it can oxidize, reduce, and exchange. So that's the reason. Benja? So Joule heating will heat for sure the region where it's occurring, and then the oxygen mobility will be higher in that region because it's hotter. So probably there will be more oxygen drift in the region close to your filament where there's Joule heating. Here it was also a way of visualizing where the filament is because it heated. So we used it as an indirect way of seeing where the filament is, but of course it will affect in your switching for sure that region will heat. And if we really believe that it's oxygen vacancies or ions, that is the same. There will be more in the region that is hotter.
Thanks for the great talk, Mónica. I had a question about the dependence of the size of your interface with the properties, with the turn-on voltage, let's say. So as I recall, when you had a large area device, it was a low potential turn-on. And then when you took it down to 5 by 5 microns, you went up to 4 volts. I didn't see the explanation of that. Is there an explanation for that effect?
So there's a reason. When I went to the smallest devices, which are the cross point, the problem is I have a voltage loss also in the electrode line where I go. So I also have to apply a voltage, an additional voltage for that line. Otherwise, it should be more. It shouldn't. So okay, in an ideal device, you're applying the voltage from here to here. However, really, normally from top to bottom, it's not linear, the voltage drop. If you have an interface, as we have, that is really oxidizing, we believe that the highest voltage drop is here because this is a semiconducting material. So even, well, I'm measuring from here to here. So I'm measuring the total voltage drop, but I don't know exactly how much drops here and how much drops here. And we believe the largest drop is in this oxynitride layer. I don't know if I've answered your question. Okay, well, then we can discuss later because I might have not understood it.
Later is very late. Any other question? Because now it looks like you don't want to leave. Okay, if not, thank you, Mónica, again.
Thank you.
I pass the mic over the director that will close the session. So I want to thank all the speakers of these sessions and all the people here.
Okay, I won't keep you any longer. I think we should go to the bar or something. I'd like to thank everyone who organized this. So it's mainly Rosa, Anna, if she's here. Yeah. Anna and Ignacy. I think it's been a fantastic day with great talks. It was great to see the invited people, but also the short talks from here, the early career researchers that gave talks I thought were wonderful. So a great vibe and a great way to celebrate our 40th anniversary. And thank you all for being here, the hardcore at the end. So thanks very much and see you tomorrow.